thanks very much for coming, everyone. So today, it is my pleasure to introduce our seminar speaker, Nick Speeney. So currently, he is a PhD student at Hopkins University in Baltimore, and he's working together with Navarro-Frenk-White.
Yeah.
And so please go and tell us about your work.
Thank you. Thanks, Alex, for the introduction. Hi, everyone. Happy to be here. Thanks for having me and letting me speak today. So the work I'll be talking about is this work about dark matter spikes and gravitational waves that I did in collaboration with Andrea, who's right there, and Emanuele and Vishal at Johns Hopkins. So a brief overview of the things I'll be talking about. So I'll give sort of like a broad view of what these dark matter spikes are, if anyone's unfamiliar. Move on to talking about kind of the work that we did with these, and then talk about the limitations of these, and also kind of the future steps, the current and future steps that we're taking to explore the limitations and, explore the future. Okay, so here's the classic picture of all the dark matter models that are out there. So of course, there are a ton of these different models. We expect dark matter to exist out there in galaxies. It helps explain things like rotation curves, lensing, plenty of other phenomena that we use dark matter to explain. And of course, as you see, there's many models. Mostly what I'll be talking about today is like the cold dark matter paradigm. But of course, spikes and sort of gravitational wave impacts using these dark matter distributions have been studied for things like primordial black holes and other paradigms as well, like the fuzzy dark matter paradigm. So what do I mean by these spikes, right? So originally, these were proposed overdensities in the dark matter due to the presence of a central massive black hole. So this was first kind of done by Gondolo and Silk in 1999. And they used it to investigate possible EM observations of self-annihilating dark matter. So if you have a higher density, this would enhance the annihilation cross-sections that you get. Yeah, but regardless of if you have annihilation or not, the existence of such an overdensity would allow for probes of the nature of dark matter through gravitational means as well. So even if you don't expect some EM signature, you can still probe the nature of dark matter with the existence of these spikes. Okay, so again, what do I mean by spikes? We start with some sort of distribution like this. So this is the NFW distribution with some initial value, right? What Gondolo and Silk kind of formulated was that if you start with this distribution and then imagine that a black hole in the center of a galaxy grows adiabatically, these particles undergo adiabatic contraction, and you get a much higher density that looks something like this. So you see relativistic and Newtonian. I'll talk more about that in a bit, the differences between these pictures. But Gondolo and Silk's original calculation used this Newtonian picture and still found this high overdensity. So this is quite an idealized case. I'll talk later again about the limitations of thinking about things using this picture. But in this idealized case, they show you get a much higher density of dark matter towards the central region, which is what we mean by these dark matter spikes. So different models of dark matter, of course, predict sort of different things, different density distributions when you consider this whole framework. So on the left here, it might be hard to see, but this is a model of self-interacting dark matter taken from Fung and others in 2021. The main change that you see are these powers of r that the density goes by. So this is r to the minus something like 1.2. What I just showed previously on that right is like r to the minus 7/3. So you get effects like different power laws for the spike if you consider different models of dark matter. Or on the right, if you consider something like self-annihilating dark matter, you actually get different shapes as well. So these plateaus are the saturation regions, if you consider something like self-annihilating dark matter, where in the center, you get so many annihilations and it depletes the density, so you get some sort of plateau. And this thing, of course, depends on what the cross-section is, the mass of the dark matter particle, things like that. So different models of the dark matter, of course, predict different things, and this might, we might be able to probe, the nature of dark matter by measuring something like the slope or the shape of these distributions. Okay, so another thing that affects, right, these spikes are, of course, the dynamics of the system. So even something like cold dark matter, of course, is affected by the dynamics of the region. So this is work by Kavanaugh and others in 2021. Even in the cold dark matter prescription, right, what they show is that if you consider the binding energy of these distributions, and then you consider what happens when a secondary object is inspiraling, particles can actually get flung away because the dynamical friction force from the secondary is too much, and then it escapes. It's too much for the binding energy to hold on to, so it escapes, and the dark matter also can get depleted. So briefly, the dashed line is like not including this effect, and then the solid lines are including this effect. So this is called halo feedback, but this is another effect that can change the spike density. So this is what I mean by saying we are considering sort of an idealized picture. There's lots of effects that can kind of change what we expect. Okay. So what our work was addressing was, given this idealized picture, right, you can still correct the spike by considering these relativistic corrections to the description of how you calculate the spike. So I'll talk about that in a second. But we were asking how important these relativistic corrections actually are, and also considering relativistic corrections to the dynamical friction force as well. As a follow-up to that, we also investigated which of these corrections are more important to actually include in the framework. A second question we ask is, how do PN terms, like in the inspiral, compare to the induced effects by the dark matter? So are they like totally dominating the PN effects, or are they subdominant? So we investigated that. And also we investigated the prospect of observing these effects. So can you detect if you have this effect of dark matter and the dynamical friction, specifically with Emery systems? Okay. So as I was saying, but a brief introduction again, right? We expect some dark matter in galaxies. And for this, we focus on the cold dark matter prescription. So we start, as I was saying, with some sort of distribution, like an NFW distribution, which was, the cold dark matter n-body solution, basically, to what the density distribution looks like. We also considered Hernquist, but you effectively get the same sort of answers when you look at the NFW and Hernquist profiles, so I won't talk about the differences between these two. And as I was saying, the distribution of this dark matter changes near the center, right? So we get some spike that looks like this. And now to go into what I mean by these relativistic corrections, right? So the blue curve is the original Gondolo and Silk formulation of this adiabatic growth problem. But importantly, it gets wrong this region that's close to the central object. And this region is very important to get correct for doing things like gravitational wave science, right? you get a lot of signal in this region. So you really need to get this correct to understand what the actual signal will look like. So doing this relativistically, you actually get a density that goes in further towards the central object, right? So this blue curve actually drops off at 4 times the Schwarzschild radius. But if you treat it relativistically, the density can go all the way to 2 times the Schwarzschild radius. So it gets much closer. And there's also a bit of a higher density as well. Right? So this red curve is a bit higher in between. This region is important for Imry and Emery gravitational waves. So this is what I mean by the relativistic correction to the spike. So what we do with these spikes, so briefly, I don't know if I had here, but you see there's these parameters rho naught and A. Rho naught is a density scale, and A is a length scale for the distribution. So to first, as a first thing we do, we investigated what happens when you change rho naught and A, right? And we basically find some effective scaling laws that I'll talk about in a second. But this left plot is showing when you change the value of rho naught, you basically just shift up and down this curve, which I guess makes sense, right? If you change the density scale, then you just change the final density scale as well. I guess maybe more interestingly, if you change the central black hole mass, you also shift things up and down. Excuse me. But maybe it's hard to see with the colors. If you increase the central black hole mass, the density actually decreases downward. So these are pretty like well-defined shifts up and down. So using these catalogs of the spikes that we generate, we find scaling laws that look something like this. So the reason we want to find scaling laws is because it actually takes a while to generate those curves, because you have to do some numerical integrations, and it takes on the order of like a day to properly find all the points. So finding scaling laws, of course, simplifies this process of generating new spikes if you want to add in some extra parameter, right? So we take that catalog that we generated and we numerically fit it and find this effective scaling. Excuse me. So this depends on rho naught, which is the scale density, the central black hole mass, and then the scale length. These exponents are found through the fitting. I won't go into exactly the numbers. And we also have this rho bar, which is basically telling us what the shape of this distribution is. So it has some overall normalization by the A. And then this eta parameter controls whether or not we're talking about the Newtonian spike or the relativistic spike. So if we set eta equal to 1, this is the Newtonian spike. Sorry, relativistic spike. We set eta equal to 2, this is the Newtonian spike. It's not super important to remember that, but basically the message I'm trying to say is that we have different fits for the Newtonian and relativistic, and then we can separately turn on and off the relativistic correction, basically. Okay, so the second bit of this is the circular binary problem, right? So in the presence of some matter there, like the density spike, we have 2 major effects that come into play, right? So first, the mass of the dark matter changes the potential that you would see. So this is controlled by the shape of the profile and the overall density, right? And then, of course, the particles also introduce a dynamical friction force. This dynamical friction force is controlled, of course, by the density, since the formula is directly proportional to rho of r. But it's also controlled by the model of dark matter we use. So I'll touch on it a bit towards the end, but I mean, if you have fuzzy dark matter, you have a different prescription for the dynamical friction versus cold dark matter, etc. But for cold dark matter, what people typically use is the Chandrasekhar formula. However, we can add in some relativistic corrections to this, right? So both of the effects of the potential changing and the dynamical friction can be treated relativistically. So with the dark matter potential change, you just use the relativistic spike that I talked about, and then you treat this as a perturbation in the orbit. For the dynamical friction, though, you can introduce these relativistic corrections to the Chandra force, which look like this C, which is a function of the velocity. So what this takes into account is, sorry, let me back up. So the standard prescription for dynamical friction, right, is that you get a wake of particles behind the secondary object, and this slows down the secondary object, right? The relativistic correction takes into account that these densities look different in the rest frame of the secondary object. And it also takes into account the difference in the scattering angle of the particles when you have relativistic velocities. This zeta is something we put in there just to turn on and off the relativistic correction again. So zeta equals 0 basically sets this whole function equal to 1, and then that's turning off the relativistic correction. But making that 1 is turning on the relativistic correction. Right? So this is, again, something we can separately turn on and off as we investigate the different effects. Okay, so putting all the pieces together and churning through the calculation, just as a first stab at seeing what effects are more important, we calculate the frequency evolution of the binary, right? And we get something like this, and the functions, these 0th and first order functions are a bit complicated, so I'm not presenting what they are. But basically the 0th order takes into account the standard GR contribution to the frequency evolution, which is just the normal gravitational wave energy loss. But it also takes into account the dynamical friction. So the dynamical friction's contribution comes in at the 0th order as well. And I should say the expansion parameter we're using is this mass of the dark matter divided by the central black hole mass. You can check for all the radii that we consider. This is a very small number, so we can use it as an expansion parameter. The first order, this is where you see the change in the gravitational potential due to the dark matter. And then you also get a dynamical friction contribution at the first order as well. So this is what we investigate, and then we use this then to calculate something like the number of cycles, right? So the number of cycles, F over F dot, so we can plug this in. And we use this to get an estimate of which relativistic effects are more important to include. So what we're doing in these plots are we're comparing the pure Newtonian description, so Newtonian dark matter and Newtonian dynamical friction. We're comparing this to separately turning on and off the relativistic corrections, and basically seeing which thing causes the biggest difference, right? So these dashed lines are all the lowest on these plots. You can barely see this one. And this is just considering the relativistic dynamical friction. So this is not correcting the density, just the dynamical friction. And this is the least different from the Newtonian prescription. So this is kind of telling us that it's more important to get the spike correct. So you're seeing a biggest difference in the Newtonian picture if you get the spike more correct, which is what the middle and top curves are basically showing us. We add in the relativistic spike, and you get even more of a difference from the pure Newtonian description. So kind of the hierarchy of these things is saying that it's more important to include the relativistic dark matter spike because this changes what you expect from the Newtonian picture the most, basically. And this is because the dynamical friction in the spike builds up quite a lot of cycles. And then if you increase the range of where you can build up the dynamical friction force, it has an even bigger impact. So it's more important to get the spike correct. So one of the questions I was asking was, of course, how important are these corrections? Important. The corrections were inducing, I don't think I pointed out, but a difference of hundreds maybe of cycles compared to the pure Newtonian description. You can get hundreds of cycles of difference. So they're important to include. And then also the relativistic dark matter density is more important since this dynamical friction is directly proportional to the density. You get more of an effect on the number of cycles through this process, so you need to get the density correct. Okay, so the second question was how PN terms compare to these dark matter induced effects, right? So, sorry, I'm looking at the time. So we also investigated the number of cycles and compared these to the 0 PN, 1 PN, 2 PN contributions to the number of cycles. Here, though, we separated out the contributions from the dynamical friction, and then this red curve is the contributions from the change in the potential, actually. And I guess interestingly, what we see here is that the contributions from the dynamical friction force can actually start dominating the 2 PN level contributions. So if you start observing things for more than roughly a year, including this dynamical friction effect starts to become more and more important compared to including 2 PN level corrections. And we do this comparison because it's not really clear where the dynamical friction force would come into play in a PN sort of picture, because it's a negative PN effect, so it's kind of uncertain how important it is compared to the other ones. But this is showing it can dominate at the 2 PN level. An important caveat of this is that this is really dependent on the masses that we choose, so the primary and secondary mass. So here we're doing 10 to the 5 as the primary and 100 as the secondary mass. But if you change these blue and red curves can shift a lot down or even more up. But we never really saw a crossing with the 1 PN level. It's more only at the 2 PN level that we saw with all the parameters that we considered. Okay, so I guess the answer to the second question, dynamical friction contributions. Yeah.
To which rate, sorry, depth of radius of the orbit, to which rate does that correspond? If I transform this frequency orbitally. Just like
I don't, not off the top of my head. It's pretty far in though, because using these masses. I'm not off the top of my head. I can plug it into the mathematical.
But also, how should I interpret this number of cycles as function of frequencies? Like, if the initial frequency is this, that corresponds to radius, and you will have that number of cycles.
Yes. So this is the formula we're using. So we're starting an observation, say, at some frequency and tracking it all the way to the ISCO, like the merger. So as we move to the left, this is more and more observation time, basically. So if you're decreasing the frequency, it's moving further out, and then we're assuming that you track this all the way to the chirp. Okay, so now let's move on to, can we detect these things? And to kind of investigate that, we employed the fast Emery waveform package, FEW, as part of the black hole perturbation toolkit, to investigate the detectability with LISA. So what we do in the codes is we introduce the dynamical friction as a torque in this manner. So we just change the gravitational wave flux and add in this torque. We use quasi-circular Schwarzschild orbits just to kind of investigate the very standard vanilla case. Here's where it's very nice to have those dark matter model fits, because it speeds up this process quite a lot. We can just plug in any parameters we want and use the spike that we need for the dynamical friction. And this goes directly into the FEW framework. a major advantage of this is that it's very quick. So this allows for rapid waveform generation, which is vital for things like parameter estimation studies. Okay, so using this, we first look at the dephasings that we would see for some reasonable observation timescales with something like Lisa. So this plot is comparing the pure Newtonian description. So the Newtonian spike is this greenish yellow versus including the relativistic spike. And I guess as we would expect, if you include the relativistic spike, you get a much higher dephasing for even shorter years of observation. And you can see the SNR, which is tracked at each year, is pretty high. So it seems like these significant dephasings occur on reasonable observational timescales. And this is also showing that, you know, as we would expect, including the relativistic spike induces more of a dephasing, even on this 4-year timescale. From this, we add in then the relativistic dynamical friction, right? So now we're both of these are using the relativistic spike, but then using the relativistic dynamical friction increases the dephasing compared to the standard vacuum case. So I guess what this is showing is using all of the relativistic corrections kind of improves your dephasing, improves the chances of detecting something. And then also not including these effects could cause a signal to be missed. Maybe if you have too much dephasing, of course, and you do something like a search, then you might miss the signal because you're not looking in the right way. Without including these effects, you're not looking at the correct wave. Okay, so we also did a mismatch analysis, right? So we looked at the mismatch and varied these parameters rho naught and A to see if, you know, you have a high enough mismatch for reasonable choices of these parameters. And it seems to suggest that, yeah, you do have a high enough mismatch to detect these things. So here, this mismatch of 0.03 is like roughly a level you might be able to detect. And then above this, so from like 10 to the -3, which is a very small choice of rho naught, and above, you see the mismatch gets quite high. And then also for this length scale, which is a bit more uncertain, the choice of this is a bit more uncertain. It's dependent on what kind of galaxy you look at or what central black hole mass you look at. But for reasonable choices of this, your mismatch becomes quite high. And then also, again, as we kind of expect, using all of the relativistic corrections of these solid lines gives us the highest mismatch. So it indicates that we could have these detectable effects for reasonable choices of these parameters, but, you know, more careful parameter estimation studies should probably be done with more generic waveforms than just the quasi-circular case to actually investigate something like the measurability of these parameters. Okay. So I guess this last question, right? Can we observe these effects with MRIs? So I guess I should have specified we were using MRI systems to investigate something like 10 to the 6 as a central mass and 10 solar masses as the secondary. So can we investigate these with MRIs? The mismatch analysis and dephasing suggests, yes, we can probably detect these. But again, the caveat, the system is very idealized. More careful study should be done. Okay. So limitations. I've mentioned some of these a bit, but let me, briefly go over these. We use a highly idealized spike density. We expect realistic spikes to have some level of quenching, which lessens the density. So quenching can come from things like core scouring, from the stars in the center of a galaxy. Also, major merger events you would expect to disrupt the spike. and cause the density to not look like the spikes we were using. So this is one limitation. We use this highly idealized model. We're also limited in the range of the central black hole masses that we consider. So this halo feedback mechanism that I was talking about before is more prevalent for lower mass central black holes, and that's because they have less of a potential well. So it's easier for particles to get kicked out of them if you have dynamical friction. So we're limited to really only saying anything about masses above 10 to the 6 or 10 to the 5, 10 to the 6 as the central object. To investigate lower mass central objects, we would need to really incorporate this halo feedback. And also, as I was mentioning, we're limited to the cold dark matter prescription, right? So ultralight boson dark matter could have a different impact on the binary dynamics. So Rodrigo showed that you have this different relativistic formula for the dynamical friction if you have some sort of different prescription like ultralight bosons. So this is one limitation that we're seeing. Oh, there we go. So some of the current work which addresses some of these limitations, but some is more like a future not really addressing these limitations. We can consider the measurability of these things, of these spikes, given some density of dark matter, right? So how high would these spike need to be to like accurately measure things or even detect them? So I showed, and mentioned several effects that quench the level of this density. If you have too low of a density, you might not have enough of a difference in the signal to actually detect that there's some sort of environmental effect going on. And especially things like the annihilation that I showed. If this level of annihilation, if this plateau is too low, then you might not even be able to detect that dark matter is having some effect on the binary dynamics. I guess another question along this direction is, can we select for dark matter models this way if we are able to measure something like the shape of this distribution? Can we actually make statements on the nature of dark matter? This seems kind of like an open thing. I mean, it's sort of in the future work that we may want to do. Another important line of current work is, what are the rates of MREs that we would expect to actually be affected by something like a dark matter overdensity? So what I mentioned is that mergers, for example, can deplete the spike density. You might expect then that the density could relax back to its spiky nature. But if you have too many merger events that are disrupting this, it might never get a chance to relax back to its spike nature, right? And you might expect that you see like 0 MREs that are actually affected by something like a dark matter overdensity. So this is an important question we sort of are currently working on, and I think others are working on as well, some different groups. And then lastly, I guess, can we distinguish between other environmental effects like accretion? So one idea in this direction is to try to write that torque that I was talking about, the E dot, dF over E dot gravitational wave. That was a torque in the few codes. But if we ignore that it's dynamical friction and just say agnostically that we have something that is some amplitude and some Pn orders, right? A r to the n as your torque. And then you have some gravitational wave signal. Could you actually make a statement on the amplitude and the slope of this? And then from those amplitude and slope, could you actually say what kind of environmental effect is going on? So you would maybe expect that dynamical friction and something like accretion would come in at different Pn orders or something. And if you measure this, maybe you could tell apart the differences. There are some questions on whether or not you can even write something like this. This is kind of like the simplest thing you could do, but obviously this form doesn't look like a r to the n because you have a lot of different r's. But this is something we may want to investigate. Yeah. I think onto the big one. Okay. Yeah, accretion disk. Yeah.
Both have a similar effect because both are expected to slow down in the picture in the Schwarzschild center. Both have dynamical friction. However, the hope is so if you have dynamical friction, you have the same sort, right? And it would appear more or less like the dark matter, just different after the The hope is that maybe one can distinguish other applications that take different forms. That would predict differently and then
Okay. So I said this would be short, probably. So to kind of summarize and conclude a bit, relativistic corrections, the dark matter and the dynamical friction can lead to considerable differences in the dephasing, the number of gravitational wave cycles. We should include these in phenomenological models to fully investigate the parameter space things. Right? As I was saying, we're using an idealized picture, but still to include all effects, you should probably consider these things as well. The dark matter induced effects can become comparable to the 2pn contributions to the number of cycles. This is highly dependent on the choices of the primary and secondary mass that you use. But this can happen on reasonable observation timescales and for reasonable choices of the mass. And then mismatch analyses suggests that the dark matter and dynamical friction effects could be detectable with LISA. Again, the caveat here is that you should do a more comprehensive parameter estimation study to see actually if you can measure specifically things like the slope of the dark matter or something like this. There's still many questions to investigate on both the modeling and data analysis sides. So I would love to discuss some of these things if anyone wants to. But with that, thank you.
Thank you very much, Nick. And now, do you have any questions?
it's not just when you fit. So all the labels in central labels can affect also the profile.
Yeah, so it can. This has been investigated by, I think, Cliff Will and others. It more or less looks about the same. When you include spin, it more or less looks the same, except now instead of some sharp drop off here, it actually can get even closer. So you have the particle orbits can get even closer. Yeah, and this would enhance things like the SNR because you have more, more orbits than in the spin case.
Also, how does it affect the shape of the, how is it still roughly spherical?
Actually, this is a bit different too. I think it's more like a shape like this.
But then maybe it's a way to distinguish between accretion disk and dark matter, because I guess the accretion disk is much flatter.
Suppose if you add an eccentricity to
Yeah, like before in the plane.
So yeah, do you think that the level of positive actually so the competition have And I mean, that's quite simple, right? Like, because every time you work on stuff, you always right, idealize things.
Yeah.
Fraction. But of course, the reality will be that all these very eccentric and well, we all know it's like that for different primers. So it's people that you think you can affect and then the very realistic.
I got a lot more pessimistic about it after the environmental effects conference in Rome 2 weeks ago. I think it would be very hard. Like, certainly, that's why I keep saying this is very idealized, because it is, and you would, I guess, need to include a lot more for, you know, the Kerr case, and I'm not sure if there would be degeneracies that would happen with things like parameter estimation when you start including eccentricity and inclination. To actually measure these, I think it's a bit optimistic. This is what I've started thinking recently, because I'm not so sure that with all these effects that can quench the spike, I'm not so sure that you would get something that is very measurable, or if these things even are out there at all.
Yeah, other questions? Then maybe I can ask a very naive one. So now the topic of spin came up, and now you also. So I was wondering what type of other effects. And you probably already mentioned some of those in the conclusions or the limitations slide. But like other options that could change considerably the kind of profiles you're looking for. Yeah, from what you've learned.
Like specifically what could change the shape of the profile?
Yeah, or have the biggest impact, or the things that we may even not know how that would work.
I think the biggest impact, I mean, I guess it depends on the model, but I mean, in this cold dark matter picture, I think the biggest impact is things like if there is a major merger event. I mean, which I guess you would expect for Emery's or something, or like galactic central black holes. These would presumably disrupt the spike, and then there's some time scale for the particles to then relax back to a configuration like that. But I mean, I don't remember off the top of my head. There's a comparison between the time scales of, you know, how many mergers happen versus the relaxation time.
Okay.
I think this also quartz counting plays a big role.
What you were saying before. Probably, if you want to find dark matter spike, you have to go through first ruling out in an agnostic sense whether there is an environmental effect, step one, and step two, whether that effect is from accretion. And only if you rule out these two possibilities, which may be hard, then you can start investigating whether it's dark matter. This is my opinion, by the way. And the reason being, first of all, that you would have this, by the way, sorry that I hijacked this. You have the amplitude and the slope, right? A and N. If you want an agnostic measurement of those, first you need to rule out when you're in waveforms, when you do a parameter estimation study, you need to rule out that what you're seeing is not due to any systematic effect, which may be hard in itself with Emery's because you know they are a complete mess. Once you ruled out this and you have a measurement of A and N, then the first needed thing, I guess, would be to say that it's an environmental effect that comes from accretion. rather than jumping into, okay, it's dark matter. Because at least in accretion, we already see the AGMs. We know there is some form of accretion going on. But if these two, you root them out, which may be hard because the models of accretion predict different, vastly different models for the plot. But if you pin this down, then you can start adding, that you can start wondering whether it comes from a spike. And if you want to test dark matters, another layer.
Any other questions? Last chance. No? Okay, then let's take a speak again.
If you enjoyed the video, like and subscribe.